My name is Brad Bradshaw. I'm president of the Hydrogen Energy Center and president of Valerity, a consulting company. And we have been very happy, pleased to put on these webinars on a number of topics. The Hydrogen Energy Center has been in existence for 25 years, focused on enabling the renewable energy revolution with hydrogen. And the world is finally caught up to the Hydrogen Energy Center. Today, we have a number of topics. We will welcome any questions you may have. Please use the chat box function to enter your questions as we go along through the session. And we'll make an effort at the end to answer every single one that pops up as best we can. This is the list of topics that we're going to cover today, the core content of today's session. We'll look at carbon emissions by sector in the United States. We'll look at what the drivers are that are pushing hydrogen to be a fuel for power generation. We'll look at use cases, the patterns that have emerged in terms of how people are pursuing producing power with hydrogen. And we have case studies of 12 hydrogen power generation projects around the world. We also will provide some illustrative economics, and we should underline, capitalize the word illustrative, just to provide some insight into how the financial flows go with these types of projects. And finally, we'll close with some discussion of the technologies that are being pursued, mostly the turbines by the major manufacturers, as well as Bloom Energy's entry into this field with a pure hydrogen solid oxide fuel cell solution. HEC is a non-profit professional society, again, focused on accelerating the renewable energy economy with hydrogen as an enabling solution. We are a membership-driven organization, and so we welcome members. We've had quite a few members sign up recently. Frank Zamataro, somebody who I interacted with easily 15 years ago in the clean energy space, Shannon Scott, Arshdeep Kaur, John Bailey, Jerry Runte, and quite a few others. So welcome to the Hydrogen Energy Center. I look forward to working with you as we go forward. The upcoming hydrogen sessions. This week is the grid scale hydrogen power generation. Next week, we're going to look at the global trade developing in hydrogen, large scale transport of hydrogen in liquid form, gaseous form, ammonia, as well as liquid organic hydrogen carriers. We'll be doing a deep dive on water splitting and electrolysis. And a few weeks from now, we'll look at hydrogen production with carbon separation. A number of different efforts are being made to make that process more efficient and easier to deal with the carbon. We'll be speaking at the end of June on wind to hydrogen, which is a fairly large development in the industry, mostly in Europe. Valerity provides consulting to energy companies and technology companies, mostly in terms of understanding markets and translating markets into actionable strategies. We have been doing some work in the gas field, the renewable gas field, which is fast developing, and I think is the next phase of the clean energy efforts in the United States. We're going to finish the task of cleaning up our electrons, but we also have to transition to cleaning up our molecules, and hydrogen and other renewable gases are a key part of that energy transition. I've worked with some of the larger energy companies in the United States and in different parts of the world, as well as companies that Ken Brown represents, such as Safe Hydrogen, work even with Beacon Power in terms of transitioning their strategy to growth opportunity back in the day. So with that introduction, we'll launch into today's discussion about using hydrogen for generating power. We can see in the different sectors, the red line at the top of this chart is the emissions associated with electric power production in the United States. And we can see a peak of around 2006, 2007, with the Great Recession then beginning a decline. And we see that the electric power industry has really led our economy in terms of carbon reduction. We can see why the focus is shifting to other sectors, but I think it's also important to recognize and understand what it is that's been driving this reduction. This chart, let me explain it because it looks a little confusing perhaps, but every year, we produce 4,000, we produce billions of kilowatt hours per year in the United States. And that's the vertical chart on the left side. We also have a black line that moves through the chart, which is the Henry Hub price for natural gas. We can see that natural gas was up around $9 per MMBTU in 2008. And then it dropped rather drastically with the Great Recession and then kept a fairly low profile. In fact, continued to decline from 2009 to now. And the large reason for that decline in the natural gas prices has been the fracking industry that has resulted in a deluge of natural gas on the market at prices that volumes and prices that really drove it down. We can see, right now natural gas is perhaps around $2.60 per MMBTU, maybe a little higher. There's been some firming in that market, but we can also see something else that has happened in this transition. The blue bars along the bottom of the chart, that is coal-fired generation. And you can see that up till about 2008, coal represented pretty nearly half of our power generation in the United States. Right now, you can see that it's perhaps around 20% of our power generation, and it really has declined. And the carbon emissions associated with coal are fairly high per unit of electricity generated. And so we can see that the real reason, the primary force that has dropped carbon emissions in the electric power sector has been shale gas. Shale gas with low price really gave an economic thrust to the combined cycle gas turbines that are burning the natural gas and producing power. And the way our industry is structured is that it's a merit order based on the marginal cost of production. So the economics of natural gas really improved from a marginal cost of production perspective, and it began to edge out coal significantly. We do see some growth in the green bar at the top of the chart, which is the renewable energy, but it looks like it's gone kind of slow compared to the way natural gas moved. And so this is where the emphasis is going to be going forward. If we're really going to get to net zero in the power sector by 2035, as some people are offering, there's really going to have to be a jump, because we've been, dancing with gravy, so to speak, with the great fracking revolution that has really dropped the carbon emissions in the electric sector, and we need to pull another rabbit out of the hat, per se. What are the factors that are driving the interest in generating power with hydrogen? The first is the increasing pressure to accelerate power grid decarbonization. Efforts are going to continue to push carbon out of the power system. This is happening globally, and in Europe, perhaps a little bit more purposeful than in the United States at this point, and that the power generators see the risk of their assets being stranded, especially with the prospects of putting new power systems in place. We are seeing canceling of coal plants around the world in terms of plans to finance and build coal plants. But we're also seeing the beginnings of that effort on the natural gas sector. And so something else is going to be needed there. We also see the increasing renewable energy creating challenges for grid stability and calls for dispatchable fuel-based energy solutions. The storage capabilities are significant in terms of lithium ion, but the scale opportunity and the longer duration beyond half a day is very challenging economically for lithium ion batteries. We've seen lithium ion increase its role from 2 hour to 4 hour to 6 hour now as being a standard in the duration of storage. And we are going to see that in the next 8 years or so expand to a standard of about 12 hours of duration. But we're going to need days, weeks, months of energy storage in order to complement the vast amounts of renewable energy going on the grid. The other real core element in enabling hydrogen in the energy picture is the economics of electricity. And the economics of electricity on the grid are changing radically. Last year, it was claimed that the lowest cost electricity in history is now emerging due to the solar energy projects that are going in. You take a place with high insolation like Saudi Arabia or India, and we're seeing prices approach a penny per kilowatt hour on a power purchase agreement basis, and that's an extraordinary low price. Right now, we do know that Arizona Public Service has offered something close to 3-cent power to Nikola, and that is extraordinary because that enables $1.50 per kilogram hydrogen. And that's the relationship we're talking about. If you can get to $2 kWh on a long-term full year basis for producing hydrogen, your marginal cost of production with an electrolyzer starting with 2-cent power is $1 a kilogram. That's very compelling from a hydrogen production perspective. Without that capability, this would all be for naught, essentially. And we're also seeing that I've seen some estimates that curtailment could be as high as 20% of full power generation in the United States if we, as we shift to more and more renewable energy. That's a high number, but granted, we're already curtailing several million megawatt hours in California, and this is just going to continue where we're going to have vast amounts of oversupply at different times of day and different times of the year, and it creates an opportunity to capture those stranded electrons and to do something with them. And I do want to point that it's not just solar and wind, but the hydropower people are facing this challenge of curtailment as well across the United States that I'm aware of. And finally, there are technologies that use gas for producing power that are extremely well developed, but also you look at companies such as Siemens and General Electric and others that have huge investment risk overhangs basically in their fossil turbine businesses. And they have been making efforts for several decades, in fact, to enable these turbines to run first on a mix of hydrogen and natural gas, and then to be able to run on 100% hydrogen as well. They have been making these efforts quietly behind the scenes as we move along. This is not a big surprise for those major suppliers. This is an opportunity and a risk that they're addressing in their businesses. It is interesting that the combined cycle gas turbines can have efficiencies as high as 63%. There are some modifications with the turbines with hydrogen, so I don't know exactly how high the efficiency can go with hydrogen. I think I'm aware that it's close. It does need to be tested and evaluated, certainly. But this is the competition for fuel cells in order to achieve these kinds of efficiencies, which I think some of them can, but we have some data on that back in the presentation. The use cases that we are seeing when we look specifically at actual projects, and we're going to be talking about 12 specific projects in this presentation. And there's no rhyme or reason for inclusion or exclusion. These are the projects that either have already been built or they're projects that are in the advanced planning stages. And what we've seen emerge is really the first three. The fourth is kind of a next stage of the development. But most of the projects, half of the projects that we see, are capturing excess hydrogen from industrial processes. And of the 6 projects we've identified that are doing that, 5 of them are taking hydrogen from chlor-alkali plants. Chlorine is a major industrial gas, and the production of chlorine is done with chlor-alkali, which are big electrolyzers, and they produce hydrogen as an output. For example, one of the industrial gas companies in New York State takes in hydrogen from a chlor-alkali plant in Niagara Falls, New York, and actually liquefies it and sells it as an industrial gas. But we have cases where this hydrogen has been turned into electricity and then used to feed power to the chlor-alkali plant itself on an in-the-fence power generation application. The other approaches we're seeing is the use of steam methane reforming and also the ATR systems using the stream of methane, natural gas, and converting it to hydrogen, running a power plant on that hydrogen, and then taking the CO2, separating and sequestering that CO2. These are projects that we're seeing in the industrial belts in Northern Europe that are at the landing spots for the North Sea oil and gas assets, because it makes it easier to turn that CO2 around and pump it into abandoned wells for sequestration. We're seeing plans for decarbonizing the grid in Europe, which include a combination of hydrogen produced from renewable energy and electrolysis, as well as hydrogen produced from steam methane reforming and ATR systems that then separate and sequester the CO2. It's a strategy which allows existing assets to be mostly remain in place, which is an interest on the part of many companies with these asset overhangs. The third case that we're seeing more emerge is the production of hydrogen from renewable energy, and then the storage of that hydrogen in large underground salt caverns, and then to feed that hydrogen back into a power system to produce power during the times of high demand for power and low supply of variable renewable energy. Very challenging economics on those systems, and the scale is just tremendous. I mean, we're talking, multi-months of energy storage. Finally, the one I wanted to put here, which I think is an early stage, but a lot of resources are going into this, which is methane pyrolysis. And methane pyrolysis is where you use a 900-degree chamber to separate the elements in methane and precipitate out elemental carbon. There's a large plant in Lincoln, Nebraska, which is doing this to produce carbon black. The hydrogen is then going to be used, I think, in ammonia production down the line. So it's not power production per se, but it is a strategy that produces elemental carbon, which is easier to sequester than gaseous carbon dioxide. And so I think we'll see developments in this area. The 12 plants that we'll be speaking about today are located around the world. Of course, half of them are in Korea, or nearly half. And you can see there are 4 in Europe, 1 in the United States, 2 in Australia. There's also 1 plant of note in China as well. Again, as I mentioned, 6 of these projects are using byproduct hydrogen, and the total size of those projects is about 72 megawatts. The total of these projects, as you can see, is 3,300 megawatts. So the byproduct hydrogen products tend to be smaller on average, 10 or 11 megawatts in size. The renewable energy and storage, that's a lion's share. 3 projects, 1,800 megawatts, very, very large projects. We're also seeing the SMR plus CCS, steam methane reforming plus carbon capture and storage or sequestration, fairly large projects as well, roughly 650, 700 megawatts per project. We have 1 project in here which we just don't have information on, but it is important to have it in. I think this one is in China, and the information is fairly unavailable on that project. Here are the 6 projects that use recycled hydrogen or excess hydrogen produced from industrial processes. It's a compelling solution. There was a project put in Fusina, Italy, which has been in place for over 10 years. The CEO of the company associated with that project will basically say the electricity is way too expensive. They have kept it operating. I think it was a very expensive project, and they're using excess hydrogen from a cracker, and they're using a GE turbine to produce electricity. And I think the price of that electricity is, up at, I think they've got it down to about 10 cents a kilowatt hour at this point. Doesn't sound too bad. That's the only turbine, interestingly enough, in this set. Most of these projects use fuel cells, and we see some PEM fuel cells, solid oxide fuel cells, and some unspecified ones as well. So this seems to be a fuel cell type application. The scale lends itself to that. Smaller projects, the turbines are probably get a little bit too expensive to make the numbers work. The Most of these are called in the fence because the electricity just goes right back to the industrial customer. It doesn't go out to the grid. Uh, that's not to say it doesn't in some cases, but a kilowatt hour saved is a good idea. And why buy from the utility if you can produce it yourself as well? So that's what we see. The very basic information here shows 27 tons a day of hydrogen, $1 a kilogram to buy that hydrogen from the industrial facility. You can see the production of kilowatt hours per year from the fuel cell, and a sale price of the electricity at 10 cents back to the industrial customer. It's about a 10 megawatt fuel cell in this illustrative model. Fuel cell efficiency at about 50%. And I recognize I've seen, there are numbers that bounce around that 50%. So for a $20 million investment and an 8% discount rate, you can see that it's a, slightly positive NPV. Just to give you a sense of what it takes to get this kind of project moving in terms of the cost of the hydrogen and the cost of the electricity. The projects for the renewable energy, the Intermountain project is one that has gained a lot of press and recognition. There's also two projects in Australia. The Port Lincoln project, you can see, is quite a bit smaller. In fact, it's almost a test case. It includes a 10 megawatt turbine and a 5 megawatt fuel cell, so sort of a combo play. The Project NEO project in Australia, that's a very large project, 1,000 megawatt. And they mentioned using fuel cells, and I just think that's something they're going to find out is not the way to go as they move forward, and they'll probably shift to a turbine strategy. The economics on these projects are very challenging, and there are a lot of pieces, and all the pieces have to not only work well together, but there has to be a Herculean effort to get the efficiencies up of each step in the process. The steps in the process include going from renewable electricity on the left side to renewable electricity on the right side of this chart. And there's a lot of activity in between those two. And what does that activity end up doing? It ends up just eating away. You can see fundamentally that if you're taking in 1 million megawatt hours a year of renewable electricity, you're putting out 423,000 megawatt hours of renewable electricity on the other end of the day. So it's that's a 42%, efficiency in terms of the in and the out. The capital investment in this particular model, and again, these numbers are just illustrative, just to give you a sense of some of the scale and some of the efficiencies. But you can see that it's a $300 million project. And to get the NPV positive requires basically a 2-cent buy on the renewable electricity and a 16-cent sell on the electricity produced from this system. It's also important to point out on these systems that if it's really a storage play, you certainly can't take energy in at the same time you're putting energy out. It makes 0 sense to do that. What that means is that you're only going to be operating the incoming energy for 50% of the time and the outgoing energy for 50% of the time. Maybe some changes in that, but that's kind of the max that you can envision. This particular model is 45% capacity factor on the incoming and 45% capacity factor on the outgoing. So this is just to point out that a storage solution of this scale is not a truly dispatchable system. dispatchable when you need the power during the high price regimes, but it's not dispatchable like a fuel-based power plant that's going to be operating anywhere from 65 to 90% of the time. But that's the role it's going to play. It's a seasonal storage, it's a long duration storage solution, and it really requires a fairly large gulf between the electricity price in and the electricity price out. The plants that we see with the SMR strategy with carbon capture and sequestration, again, these are in Great Britain and the Netherlands, located near the North Sea, and they are plants that they are going to repower. They're existing plants, which they are going to modify by putting in a hydrogen turbine, hydrogen-powered turbine, and using SMR to produce the hydrogen and capture and sequester the carbon dioxide. I do not have any financials on these, but again, this is where there are significant assets already in place, and the trick is to see what the marginal cost is to decarbonize those assets using this type of approach. I think we're going to see a lot more of this activity going forward. We're going to go over just a few of the technologies, and then we'll open it up for questions. The Baker Hughes and General Electric are on this slide, and Baker Hughes used a GE turbine at Enel, which was the Fusina, Italy plant that was built perhaps 10 years ago. And they are using 100% hydrogen on a modified turbine back then. And down below, what we see is we see the various turbines offered by General Electric and their plans. And we can see that the BE class of turbines already is 100% hydrogen capable today. Now, there's a huge amount of activity to blend in hydrogen into natural gas and to use that blend in power production. And turbines are able to go today easily up to 30%. Many can go to 50% hydrogen by volume. But they all have done at least one turbine or several installations with 100% hydrogen capability. The reason that this is not so challenging for these companies per se is when we think of the power industry, we think of, you know, the pure fuels, the coal, the natural gas, the wind, the solar. But there are quite a few situations in industry with mixed gases being produced, which include complements of hydrogen as well as other gases. And the challenge has been before companies like General Electric and Siemens and Baker Hughes to provide these turbines the capability to run on mixed fuels, including 50% hydrogen by volume. And this has been going on for decades. And so the technicians, the engineers at these companies have a certain amount of understanding of dealing with different fuel mixes and what the implications are for the design, performance, and operation of these turbine systems. Now, I also want to point out that you know, it's not as easy just to run a turbine on natural gas and then to just say, well, we're going to switch to hydrogen. Easily said, not easily done. And there are several reasons for that. The WOBE index was brought up last week, and the truth is that hydrogen has some characteristics. It has extremely high flame speed. It actually, if you put hydrogen in another fuel and burn that fuel with hydrogen in it, you actually end up getting a more efficient burn a higher burn percentage of the fuel, it really helps in the combustion. But the flame speed is such that if you have a certain nozzle design and the fuel is entering the chamber at a certain speed, you have to change that design because hydrogen is just going to flame right back to the core nozzle, as it were. I am certainly not an expert in this field, but that nozzle design is one aspect because of the high flame speed. Now, the other aspect, and I do want to point this out, is that if you just burn hydrogen like you're burning natural gas, you will get a higher amount of NOx emissions associated with this combustion. And that fact is not lost on the technology companies that are embedded or invested in these turbines. You're not going to run around and go to the LA basin and put in a turbine that's spewing out tons of NOx. You're not going to meet the criteria for emissions. So there's a lot of work going on, and it's been ongoing in terms of methods to change the design of these turbines and to have pre-combustion elements introduced into the fuel mix, as well as post-combustion activities to mitigate and reduce the NOx emissions associated with these technologies. And so that is a necessity that is not overlooked by these major companies as it's going forward. So I did want to point out Mitsubishi has a 100% hydrogen turbine that's been operating. They're working on a number of projects. The big project in the U.S. is one of theirs, as well as the Magnum project in Great Britain, which is converting one of the 440 megawatt gas turbines to run on 100% hydrogen with the SMR and carbon capture and sequestration. And Siemens has demonstrated 100% hydrogen turbines as well. So the work is being made to mitigate NOx, and that's an important part of this process going forward. Finally, Bloom is demonstrating their nimbleness in their strategy. Bloom's energy servers, so-called, have basically run on natural gas. That's what they're designed to do. Solid oxide fuel cells have a high temperature, and they also have an ability to withstand many cycles and hours of operation at high temperatures with different materials coming through the system. So they did first begin to introduce landfill gas into their solid oxide fuel cells in order to green them up. But then they introduced last year a hydrogen-based solid oxide fuel cell. And last year, they also introduced a solid oxide electrolyzer. I don't know if you call it an SOFC electrolyzer. I think they do, but that doesn't seem to make sense to me. So they've decided to offer pure hydrogen fuel cells as well as electrolyzers to produce hydrogen as well. And they are one of the players in the projects that I identified. They're putting a lot of projects out there which run on landfill gas and run on natural gas, but they have a few, two in fact, that run on pure hydrogen. One's 100 kW and another is 1.8 megawatts. And I think they're both in Korea, where a lot of this activity is taking place. You can see the efficiency here, 52%. I get the feeling it's higher than that, but I think it just bears some calc going forward. So ready for question and answer.
So hi, Brad, it's Rick.
Hi, Rick. How are you today?
We have a question about the typical costs of cleaning up hydrogen from chloralkali for fuel cell use. I think that answer may be different depending on whether you're talking about a PEM fuel cell or a solid oxide fuel cell. but do you have any feel for what it takes to clean up the hydrogen?
No, I don't have an answer for that. I suspect that they use, because it's a higher volume activity, they probably use the pressure swing absorption approach to that in order to achieve what they're looking for. And then it's a question of what the application is, certainly going forward.
And Doug has a question about the industrial, in the loop where you showed that the hydrogen goes right back to the industrial customer, where you've got everything's behind the fence.
Yep.
Is there something with respect to the end use that gets us to that dollar and the 10-cent figures that you had on the slide? How were those generated? Doug, you're on the call. You can maybe ask some more detail about that.
Yes, and yes.
Just trying to get to the unmute. Yeah, I just meant do they have different divisions, and are they buying and selling from themselves internally? Like, why set those values if it's internal to the company? Wouldn't they just, I don't know how the company would do that transaction. Is it just one division is selling to the other?
Yeah, I mean, in the fence can also mean a third party has actually built and operates the facility, but then it's not going out to the grid, which is really the key difference. But certainly, Doug, there are many plants where a company will invest in the plant and they're not using a transfer price within the organization, but most organizations actually do use a transfer price in their accounting, and that's in order to keep things clear, certainly. But yeah, I suspect there's quite a variety of approaches that people take on that measure of accounting and who's involved.
Kenneth Brown has a comment. I think I understand it, but he's saying a fuel cell can run backwards as an electrolyzer, or maybe he's asking that as a question. I know that there have been so-called reversible fuel cells on the market, but is that a significant technology?
Yeah, Ken, if you want to unmute and ask that question, that'd be great.
The membrane electrolysis machines, particularly from Cummins and I think Plug Power are the two that come to mind, are essentially fuel cells that instead of taking in hydrogen and oxygen and giving you power, take in power and give you hydrogen and oxygen, or they essentially run backwards. They're more efficient if they're run as fuel cells than generally if they're run as electrolyzers. But I understand that Cummins has made some significant advances and are not using the high temperature alkaline electrolysis, but they're using their membrane electrolysis as the technology of choice, because the efficiencies are higher.
Yeah, I mean, that's fascinating. If there's a storage application, as we said, you're never going to be electrolyzing and producing power at the same time. So a reversible might be a way to cut capital cost.
I'm not sure that they are reversible, but essentially,
right.
you're reversing the operation of taking the two gases, combining them to make power, to taking power and producing the two gases. And I'm sure from the designs that it may not be something that you reversed. Say, 1 minute you're doing one way and the next minute you're doing the other way. I don't think that can happen, but because of various design considerations.
Mm-hmm.
So Brad, Vanessa Fox asks, why are so many of these projects in South Korea?
Yeah, I mean, they have a very aggressive fund for decarbonizing their economy, and they're putting that fund to work in power production. And they also, there's a company in Connecticut called Fuel Cell Energy. Fuel cell is written as one word and then energy. And they have been deploying multi-megawatt fuel cell systems in Korea. They've been a big partner there. And I think that, you know, Korea is also very interested in cleaning up the emissions and improving the efficiency of their power sector. So you add the carbon, you add the efficiency, and you add the emissions, general emissions cleanup, not just carbon, and it's a perfect storm of opportunity. You know, KEPCO and KNC and others are, you know, very aggressive in the partnering, and that's where we're seeing so much activity.
Frederick Clack asks, is there a greater demand for hydrogen than there is a supply? I guess that there are two ways to look at that. That's the present market, and then what we hope will be soon to come green market, where the demand for green hydrogen is going to spike. But Brad, you have a comment on the supply and demand implications of the market?
Yeah, I think if you speak to any industrial gas company, they'll tell you that the supply is larger than the demand. You know,
I can comment on that.
that'd be great. Susan, go ahead.
Here in California, there's never enough hydrogen for the fuel cell vehicles. Never. There's always a shortage. We can't wait till there's more hydrogen.
That is do you, Susan, drive a hydrogen car?
I would if the station near me had hydrogen routinely.
You know, I've only obliquely looked at that issue because I find it very disconcerting, you know, that the 120, I mean, the size of the hydrogen market globally is tremendously huge. And you look at the supply chain structure, and there was no flexibility. In other words, each station was owned and operated by an industrial gas company or had an arrangement, and that was the only supply. In other words, they weren't able, there's no, from what I can tell, there's no fluidity or, you know, it's not a fungible resource as yet. And so we have some distance to go. The real change, I'm glad you brought that up. The real, you know, we're getting to 10,000 cars in California, and we can see why one of the industrial gas companies is building a tremendously large hydrogen production facility in Nevada to feed that market. And I think that's, you know, we can't wait. Yeah. Yeah. And the other, go ahead.
For many years, one of the members of the Hydrogen Energy Center was James Provenzano from California. James is the director of Clean Air Now, and he had a hydrogen fuel cell vehicle, one of the very first ones. And he always told me he never had any trouble getting fuel for his car. But that was back in the days when you could count the number of fuel cell electric vehicles in California in single digits. And now, as you say, with 10,000 vehicles on the road, it's much more challenging, even though California has an aggressive build new stations policy.
Thanks, Susan.
I have a comment as well.
Michael? Who's that?
Yeah. Good morning, Mike Yeshuba with GoBiz here in California. And yeah, another thing that could be added is the fuel cell bus issue we have out here. There are some transit agencies that are going to be required to go to zero emission buses, and some of the transit agencies are reticent to go with you know, more or less proven fuel cell buses because of the lack of a guaranteed supply of hydrogen to fuel those fleets. So yeah, we you know, hydrogen is a motor vehicle fuel out here, and we need more.
Very, very good point.
If I may, yeah, in as much as the people here know, is there anyone working on an onboard hydrogen generation unit? I would think steam reforming makes sense. I've done some years ago when I was working in catalysis work for that, and this seems feasible. I moved on to other areas, but this seems nevertheless a very attractive option. Basically, you put in water and you get hydrogen working on either type of fuel cell available.
Yes, I mean, the United States spent $1 billion developing that technology in the early 2000s, and companies such as General Motors and others were looking at onboard reformers. I worked at Arthur D. Little, which was working on that technology, and it just, at the end of the day, it was much easier just to pipe gaseous hydrogen into a car than to do some, to run around with a chemistry plant in your car. And so we might see the emergence of a onboard methanol reforming for exactly that purpose. And there's a fellow that I used to know that had an announcement 2 weeks ago on that, where methanol seems to be another sort of interesting carrier or fuel that can be used and reformed easily. So is that Victor who's speaking?
Yes.
Okay, great.
Hi, everyone.
So let's go to another question, Rick, if we could.
Sure. Tomlin Coggeshall, who's been associated with the Hydrogen Energy Center since the mid-1990s, is curious about how the turbine generation costs compare to the fuel cell generation costs. Tomlin, you can speak for yourself, obviously, but you seem to be curious about why there's so much effort to clean up the turbines rather than to go to higher output fuel cells.
Yes, Tomlin, would you like to speak up?
Oops.
Okay, so yeah, I think that generally the turbines are higher efficiency and lower cost than the fuel cells at that scale, and I think that really is the key. We can see again the smaller applications were almost all fuel cells, and the larger applications are almost all turbines. And I think it just really has to do with the economics and the efficiencies of those systems.
Thanks, Brad. I couldn't find my unmute myself and all the people to unmute in time, but that's a great answer. But and I know Fuel Cell Energy, which you mentioned earlier, is doing a lot of grid scale work. So it's interesting. Maybe there'll be a point where the fuel cells catch up with the turbines in terms of efficiency.
Yeah, I think just to be clear, and I didn't mention at the outset of this presentation that I have I'm not excluding players for any particular reason, but Fuel Cell Energy is a fossil fuel based company, and as a consequence, they're emitting CO2. And that's not really, they don't, so it's fossil-based fuel and emitting CO2. And I think those are two elements which, the clean hydrogen approach is trying to eliminate that. And that's why we speak to the elemental carbon, or we speak to sequestration, or we speak to renewable energy produced hydrogen, because we're really stripping out the carbon of the equation. And Fuel Cell Energy, maybe they're on the call, but I haven't seen them shift yet. You saw Bloom shift. Bloom was natural gas based 100%. They shifted over to some landfill, and then they shifted over to pure hydrogen as well. So they've recognized the importance of making that transition as the industry moves forward. I'd like to see fuel cell energy do the same.
Yeah, they did have a system where they took a municipal sewage, you know, installation and pulled the methane out of that to make electricity. But I haven't studied them closely lately.
Yeah, that's a very, very good point. We're seeing that shift to, for example, Biotech is a emerging hydrogen production company using a methane reformation solution, and they've shifted over to embracing renewable methane as a fuel source in their mix to be purposeful as well. What's interesting is they'll talk about negative carbon emissions, and just so everyone's clear, if you're capturing methane, which is a very volatile greenhouse gas, and maybe at the end of the day producing some CO2, you're really changing the equation, and that's why they can claim negative on that, because they're really shifting away from a very volatile greenhouse gas. So Talman, thank you for that. Rick, do you want to identify some other questions?
Well, there was a question in the last session that came to mind as I was looking at your slide on the Intermountain project. I was very surprised at the 16 cent per kilowatt hour price that they're forecasting they will need to charge to make the project feasible economically. And the question during the last, or maybe it was 2 sessions ago, was whether or not the gap between the low cost power that they can generate and the price that they charge, whether that gap is going to close, whether it will not be feasible for them to charge 16 cents a kilowatt hour, because so many more renewables will be coming on at a lower price and maybe storing in different ways. But anyway, I just didn't know if you had a thought on how long that project could survive at 16 cents a kilowatt hour price.
Yeah, so let me be absolutely clear. First of all, the numbers in the presentation were numbers that I made up. They are not representative of that specific project.
Oh, okay.
Just to be clear. And those numbers were forced numbers to generate a positive NPV based on certain assumptions going in. The point being is just to look at some of the scale, the efficiencies, as I said, some of the things that are needed. And I'm sure there are some very fine pencil points, but to be clear, the project in Delta, Utah, they signed a long-term power purchase agreement, if that's what it's called, for natural gas through 2045. So they're planning on actually burning natural gas and then blending in some hydrogen as they go forward. So essentially keeping a minimum 65% capacity utilization of the plant for the next 20 to 25 years. So there's it's not really voodoo. It's just, there's some very smart math going on in order to make sure there's good economics. They're going to take a coal plant and install turbines. Like the numbers are something like it's a it's a 1600 megawatt coal plant. They're going to shift it down to, I don't know, 700 megawatt natural gas. But they're going to run that natural gas plant on natural gas for the next 20 years, which is basically they'll get their useful life, their return on their investment, and so on, and begin to blend in the hydrogen over time and develop the stored hydrogen solution. And then at some point go to 100% hydrogen. And again, when they go to 100% hydrogen, you're going to be a sub 50% capacity utilization on that plant. The numbers change significantly, but I think they've got 20 years to figure that out. Frankly, it looks like they're putting in a big hydrogen seasonal storage system at the outset. That's absolutely not the case. It's really going to be a natural gas-fired power plant with a hydrogen mix over time, increasing. And ultimately switching 100% hydrogen 20 years down the line. I hope that provides some clarity. First, the bells go off I'm not representing their numbers. I have no idea what their numbers are, especially for a plant that's going to be operating 20 years from now.
We have a comment from, I can't pronounce your first name, Mr. Ames. You may want to jump on to do this. You've mentioned this before about ocean water derived hydrogen as possibly managing sea level rise, and why not use it and avoid sequestration altogether. Would you like to unmute and chime in a little bit on that?
Yeah, I just feel that, well, for a long time, I've been working on ocean-derived hydrogen, and I was working on it before sea level rise was even mentioned as a problem, and I used to be worried about large-scale electrolysis, purification electrolysis of seawater would lower sea levels conceptually. And now, all these years later, 43 years later, here we have this extra water that's causing havoc on ocean islands in the Pacific, etc. There's our next fuel. If we can turn liquid into gases and sequester the liquid ocean water as hydrogen and pump down the oxygen using renewable energy to revigorate ocean dead zones, I think we have a beautiful kind of a scenario there. And I'm not hearing that discussed here as an option. I'd like to see more on that.
Yeah, one of the plants that's doing the excess hydrogen, they are actually recovering the water from the system and putting it to work. And so I think that the management of water is an important factor. I can't imagine what it would be like to have my finger in the dike of seawater rise. You know, the amount of water we'd have to take out of the ocean and do something with it to mitigate ocean level rise. That'd be an interesting calculation for it. But I think thinking about ways to clean up our water anywhere is certainly. We are seeing these combo solar hydrogen units producing electricity and producing clean water in developing countries, and it is good to see those kinds of coupled solutions to clean up the environment and address local issues. Very good, thank you. I look forward to talking with you about your work in ocean energy systems, but not necessarily this forum today. Rick, any other questions today?
Frederick asks about the costs of electrolysis, noting that electrolysis is the cleanest way to use renewables. Is there a particular cost that you're focused on, Frederick?
You mean Ford?
Hello, sir. I think I'm on. Yeah, I was just wondering, although I pronounced the word incorrectly, I was just wondering if the catalyst is too expensive. I guess they use platinum and other things, and I was just wondering if they're experimenting with different materials or something to reduce the cost and make it more viable for electrolysis. Over.
There are many questions, Frederick, because when you look at the existing commitment to deploy electrolysis in Europe, they're at a level of, I think, 40 gigawatts by 2030. It increases the size of the market, I think, by a factor of 400 times. So if anybody wants to get into a growth business, electrolysis certainly is one of the ways to go. And the demands on the supply chain and precious metals, I think I've been seeing a lot in the news in the last few weeks on the solar has been increasing in price in the last 6 months. And the reason that's been increasing is because of the extraordinary demands, the capital requirements on the supply chain, and that is a big. We're going to see that in the batteries. You start putting batteries in every car manufactured, 70 million cars a year. Right now maybe it's something less than, it's maybe 1.5 million electric cars a year. If we get to 70 million electric cars a year being produced, the demands on lithium ion precious metals and such are going to be extraordinary. So this is a key issue, and you can look it up. There are people that are looking at trying to find, non-rare earth elements to manufacture electrolyzers and fuel cells to reduce the strain on the supply chain in the resource. Very good question.
I would just like to say something for your audience. It's an idea. Part of I consider wind and solar the same thing. I think it's solar energy that causes wind. The best place to probably capture wind is far offshore for various reasons, aesthetics. It doesn't affect birds, so forth. And so I was just wondering if you could have actually real floating platforms like ships, not something that's anchored, that's, through wind is pulled through the water, generates electricity. Electricity through electrolysis produces hydrogen, and you would have a bunch of floating service vessels back and forth, because obviously you can't have an underwater cable, but you would have service vessels that also would be an extended supply chain that moves the hydrogen from these offshore floating ships to bring hydrogen back to shore, and could be converted to electricity or whatever. Over.
Yeah, Frederick, there's a group at UMass Amherst that actually has been working on that configuration, which is a boat with a windmill and producing hydrogen. I'm pretty sure that if you track what the major wind companies are doing, the floating offshore is really, offshore is now the big development that's going on, certainly here in the United States and around the world. And we're going to see a huge push forward on that. But then the next phase is the floating offshore. And that is, that is going to be very aggressive. But we're generally seeing, for example, that they've determined that it's cheaper to move hydrogen from a windmill to shore than it is to move electricity from a windmill to shore. And that's really just the cost of the cable versus the cost of the pipe. And so they're actually looking at putting electrolyzers offshore and moving hydrogen to shore. But it is interesting. There was a company was going to put windmills off the coast of Maine, and they're going to be far off the coast, more than 10, 12 miles off the coast, so they wouldn't be seen. And the state of Maine decided that that wasn't what they wanted to do. So those windmills, that project actually was installed off Scotland, and they achieved a 65% capacity utilization of those offshore windmills. The typical capacity utilization of a windmill on a mountaintop or on shore in Texas or what have you is around 34% capacity utilization. So the offshore is just a fabulous wind profile to extract energy, and in that, the size of the windmills, but the steady breeze and the higher breeze is definitely improving the economics, even though the cost of offshore can be 20 to 30% higher than onshore. But the size of the windmills is helping address that as well. It's a huge, huge, huge development. We went from 27-cent power with Cape Wind to 7-cent power with Vineyard Wind, and big change in the last 10 years in wind, certainly. So thank you for that, those comments.
Right. Just a little more on the Scotland projects. There are several in northern Scotland, and the Scots are experimenting, if you will, with the differences between the costs of shipping the hydrogen, as suggested in the last conversation, versus pipeline where it's available. And it turns out to be location specific. In some places, a pipeline makes sense. In some places, pipeline may not make sense. So even though intuitively you would think shipping would be substantially more expensive, it apparently does make sense in certain situations.
Well, fantastic. This has been a good session from my perspective. I appreciate any and all questions that come in, and if there's any reason for anybody to have a follow-up question or something they're wondering about in terms of the Hydrogen Energy Center or this, really fast-moving marketplace, we are available for you, for your inquiries, and welcome. Certainly the dialogue is just a fascinating industry. We used to joke that the hydrogen industry was 5 years coming, and it's been 5 years coming for 40 years. Well, maybe it's finally arrived. So I appreciate everybody jumping on. Rick, are we all set today, do you think?
There's only one more question if you want to take a few extra minutes to answer it or to deal with it.
Go ahead.
Tomlin's asking about using methane in high temperature solid oxide fuel cells as yet another way to deal with the methane issue. What do you do with the methane? And I've never thought about a solid oxide fuel cell as a way to eliminate methane, but do you see that as a possibility?
Well, actually, I'll chime in for a sec. I actually was just mentioning that in case anyone in the group was scratching their heads about, we're talking methane and a fuel cell, when we thought hydrogen is what you put in a fuel cell, but the solid oxide fuel cells run at a much higher temperature, which maybe all of you already know, and the methane can be used as feedstock directly with a solid oxide fuel cell, which is the type that Fuel Cell Energy produces right here in Danbury, Connecticut.
Yes,
So-
if there are any students of the Bitcoin realm, and you've got to produce your hashes and use a lot of electricity to run those calculations to generate the cryptocurrency. They're finding that you can actually take a fuel cell and put it out in a natural gas field and capture the errant methane and produce cryptocurrency. So there are some strange bedfellows out there. Tomlin, I don't know if that's where you were going with this, but you really ought to Google it for some giggles.
Yeah.
Because that's actually what's happening out
Thank you,
there.
Brad. That's interesting. Yeah.
Yeah. Yep. Rick?
I think that's, Robert Rosenberg has chimed in. Was the, Bob, what was it? What's that question about the natural gas and existing pipelines? We can separate it out. Lindy has a technology for separating natural gas. I'm sorry, separating hydrogen from a mixture of hydrogen and natural gas in a pipeline that they're trying to scale up right now. Because we have some pipelines that can't take 100% hydrogen, a lot of hydrogen that can't. But can you clarify your question a little bit?
The mute button needs to be unmuted, Robert.
Lower left, probably on your screen.
Well,
okay, we'll answer that. We'll have written answers to all the questions anyway that will be posted on the website or distributed, and I'll have an answer for Bob there.
Yeah, and I would suggest going back to our first hydrogen session, which actually discussed blending and the implications of blending, which I think is what that question is about. So, super. Well, Rick, I think we'll wrap it up.
Great.
Well,
Thanks,
thanks,
Brad.
everybody.
Thank you, Brad.
Yep, appreciate it. And we'll look forward to seeing everybody next week when we discuss the global market for shipping hydrogen around the world.
Excellent.
Thank
Great
you.
session. Thanks.
Thank you.
Thank
Thank
you.
you.